Hello friends, I welcome you in lecture number 3 on system of linear equations. In previous lecture we have discussed Gauss elimination method to solve the system of linear equations, and we have seen two cases of Gauss elimination method. We have seen one example in which the solution was unique, and we have seen one example in which system has no solution. Today we are going to discuss the example of a system which has infinite number of solutions. So for any system of linear equations, these are the only three possibilities: either system has unique solution, no solution, or infinite number of solutions. If system has solution, that system is known as consistent, and if system has no solution, it is known as inconsistent system. So if system has no solution, then in the augmented matrix, if system has no solution, then in the row echelon form of augmented matrix, you will obtain this type of row. All the entries are 0 except last entry, and last entry is non-zero. So keep in mind, if in the row echelon form of augmented matrix, if we obtain a row of this form, all the entries except last entry are 0, last entry is non-zero, and all the entries are 0. So if we obtain this type of row in row echelon form of augmented matrix, then we can say that system has no solution. And if we don't obtain this type of row in row echelon form, then system has solution. So now if system has solution, then there are two possibilities: either system has unique solution or infinite number of solutions. And we have discussed the case of unique solution in previous lecture. In this lecture we are going to discuss the case of infinitely many solutions, how to find out the infinite number of solutions using Gauss elimination method. So we start with this example. We are asked to find out the solution of this system using Gauss elimination method. So as we know, the first step of Gauss elimination method is to write augmented matrix. So the first column of augmented matrix corresponds to coefficients of x. So first we write coefficients of x, which are 1, 2, -1 and 3. Then second column corresponds to coefficients of y. So here -1, 1, 2, and there is no y in last equation. That means coefficient of y is 0. Third column for coefficients of z. So here 2, -2, -4, -3. Last column corresponds to coefficients of w. Here there is no z. This is coefficient of w. There is no z here, so coefficient of z is 0. 2, -2, -4 and 0. Then coefficients of w, which are -1, -2, 1 and -3. And the constants on the right hand side will constitute last column of the augmented matrix. So let me check again. Coefficients of x are 1, 2, -1, 3. Coefficients of y are -1, 1, 2, and there is no y here, so 0. Coefficients of z are 2, -2, -4. There is no z in the last equation, so we put 0. Coefficients of w, which are -1, -2, 1 and -3. And last column is -1, -2, 1, -3. So this is the augmented matrix corresponding to given system. So the first step of Gauss elimination method is to write augmented matrix. Now we have to convert augmented matrix into row echelon form. So this is the first non-zero entry of first row. Using this entry we have to make these three entries 0. So to make this entry 0 we have to apply the operation multiplying first row by -2 and adding in second row. Then to make this entry 0, using this entry we have to multiply first entry by 1 and add here. This is in third row. Similarly we have to multiply first entry by -3 and add in fourth row so that we obtain 0 here. So I write here. So on first row remains as it is, 1 minus 1, 2 minus 1 minus 1. Now we have to multiply first row by -2 and add here. So -2 plus 2 0, -1 into -2 which is 2 plus 1 3, 2 into -2 -4 minus 2 which is -6, -1 into -2 which is 2 and -2 0, -1 into -2 2 minus 2 0. Then we multiply first row by 1 and add in third row. So 1 minus 1 0, -1 plus 2 1, 2 minus 4 minus 2, -1 plus 1, and here also -1 plus 1. So these two entries are 0. Then multiplication of first row by -3 and adding in fourth row. So 1 into -3 which is -3 plus 3 0. Then -1 into -3 which is 3 plus 0. 2 into -3 that is -6 plus 0. So here -6. -1 into -3 which is 3 minus 3 0. Same thing here. Here we obtain 0. So we obtain this matrix which is equivalent to augmented matrix by applying these three elementary row operations. Now we come to the first non-zero entry of second row. So using this entry which is 3, we have to make these two entries 0. So to make this entry 0 we multiply this 3 by -1 by 3 so that we obtain -1 and -1 plus 1 is 0. So next operation is multiplying second row by -1 by 3 and adding in third row. To make this 0 we have to multiply this by -1 only. So multiplying second row by -1 and adding in fourth row. So third and fourth row will change and we write first two rows as it is, 1 minus 1, 2 minus 1 minus 1, then 0, 3, -6, 0, 0. Now we have to multiply second row by -1 by 3 and add in third row. So here both are 0. Then 3 into -1 by 3 which is -1 plus 1, 0. -6 into -1 by 3 that is 2 and -2. So it is 0. These entries are 0. So if we multiply by -1 by 3 we have 0 and 0 plus 0 is 0. Now we multiply second row by -1 and add in fourth row. So 0 into -1 0 plus 0, 3 into -1 -3 plus 3 0, minus 6 into minus 1, 6 and minus 6, which is 0, and these entries are 0. 0 into minus 1, 0 plus 0. So we obtain this matrix. So you can check this is in row echelon form now. This is the first non-zero entry of first row. All the entries below this are 0. This is the first non-zero entry of second row. All the entries below this are 0. And there are 2 0 rows which are below non-zero rows. So this matrix is in row echelon form, which is in row echelon form. And we know that the first column corresponds to coefficients of x. Here first column for coefficients of x, then second column for y, third and fourth for z and w. So second column corresponds to coefficients of y, third for coefficients of z, and fourth column corresponds to coefficients of w. Now we make some notes here. We define leading and free variables. Before going for solutions, we understand meaning of leading and free variables, which we require for writing infinite number of solutions. So the leading variable means the variables corresponding to first non-zero entry in row echelon form. This is the row echelon form of augmented matrix. So this is the first non-zero entry of first row, and it corresponds to variable x. Therefore x is leading variable. Similarly, the first non-zero entry of second row corresponds to variable y. So y is also leading variable, and there is no non-zero entry in third and fourth row. So we understand in this way the variables corresponding to first non-zero entries in row echelon form of a augmented matrix are known as leading variables. So here 1 corresponds to x, 3 corresponds to y. Therefore x and y are leading variables, and remaining variables are known as free variables. So the variables corresponding to the first non-zero entry of a row are known as leading variables, and remaining variables are known as free variables. So here the first non-zero entries of first and second row corresponds to the variable x and y. Therefore x and y are known as leading variables, and remaining variables z and w are free variables. So here we obtain 2 free variables and 2 leading variables. Now if system has a solution, and if we obtain at least free variable, if there exists at least one free variable, then system will have infinite number of solutions. So for infinite number of solutions, we will always have at least one free variable in the row echelon form of a augmented matrix. In earlier lecture, we have seen that the solution was unique. So if there is no free variable, then we will obtain unique solution. And if we obtain this type of row, all the entries are 0 and last entry is non-zero, then system has no solution. So if system has no solution, we will have this type of row in row echelon form of augmented matrix. So from that we can say that system has no solution. Now if there is no row of this form in row echelon form, then we have to check for leading and free variables. If all the variables become leading variable, then system has unique solution, and if we obtain at least one free variable, then system has infinite number of solutions. So here there are 4 variables in the given system, and we see that 2 variables become free variables. Therefore, this system has infinite number of solutions. So now we discuss how to write down the infinite number of solutions. So we keep in mind this definition of leading and free variables. The variables corresponding to the first non-zero entries in row echelon form of augmented matrix are called leading variables, and remaining variables are called free variables. So in this example, we can see here x and y are leading and z and w are free variables. So we obtain 2 free variables. Therefore, this system has infinite number of solutions. So now we discuss how to write down the infinite number of solutions. The first step is we have to first write down this system corresponding to row echelon form. That we can say that system can be called as reduced system or system corresponding to row echelon form. So first equation is 1 into x, that is x minus y plus 2z minus w. X minus y plus 2z minus w equal to x minus y plus 2z minus w equal to minus 1, and we give this number 1. Second equation will be 0 into x, that is 0. 3 into y minus 6z equal to 0. 3y minus 6z equal to 0. So this is this system corresponding to row echelon form, and the solution of this system is exactly the solution of given system. Now we know that this system has infinite number of solutions. Also we know that x and y are leading and z and w are free variables. So free variable means we can take any value for these 2 variables. We can assign any real number to free variables. So after writing this system corresponding to row echelon form, next step is to express leading variables in terms of free variables. Express leading variables in terms of free variables. So we start from equation 2. In equation 2 we can see y is leading variable and z is free variable. Therefore I have to write y in terms of z. Before that I can cancel out this 3. So I have y minus 2z equal to 0. Therefore I obtain y equal to 2z. So y is leading variable which is expressed in terms of free variable z. Similarly, we have to express leading variables in equation 1 in terms of free variables. Before that we will put y equal to 2z in equation 1. So by 1 we have x minus y and y we replace by 2z. So x minus 2z plus 2z minus w equal to minus 1. So therefore this minus 2z plus 2z is 0 and x minus w is minus 1. X is leading variable, so we express x in terms of w. X equal to w minus 1. So what we have done is, after writing the reduced system, we have expressed leading variables in terms of free variables. X is w minus 1, y is 2z, and z and w are free variables. Now z and w are free variables, that means we can assign any value to z and w. So we assign, let z is small r, which is any real number, and w is small s, where this r and s are any real numbers. So if we take z equal to r, w equal to s, we have, therefore we can write our solution in terms of r and s. The solution of given system is x is w minus 1, w is s, y is 2z, that means y equal to 2r, z equal to r, and s equal to w. So this is the solution of given system. Here r and s are elements of real number set. W equal to s, this we rewrite in this way, it will look nice. Value of w is s. So we can see x, y, z and w are expressed in terms of r and s, which are any real number. So for different values of r and s, we will have different values of x, y, z and w. So and r and s are any real numbers, therefore x, y, z and w will have infinite number of values. So this is the infinite solution, or given system has infinite number of solutions, which can be given by this: x equal to s minus 1, y is 2r, z is r, and w equal to s. So in this way we can write down the infinite number of solutions of given system. We just summarize this. Here we have discussed the case of Gauss elimination with infinitely many solutions. So the Gauss elimination method says that first we have to write down the augmented matrix corresponding to given system, and then we convert augmented matrix into row echelon form. In row echelon form, we concentrate on first non-zero entries of each row, and the variables corresponding to first non-zero entries are called leading variables, and remaining variables are called free variables. So in this, x and y corresponds to the first non-zero entries of first and second row. Therefore x and y are leading variables, z and w are free variables. And if there exists at least one free variable, then system has infinite number of solutions. So here we obtain two free variables, therefore given system has infinite number of solutions. If there is no free variable, then given system will have unique solution. And if we have this type of row, all the entries are 0 except last entry non-zero. So if we obtain this type of row in the row echelon form of augmented matrix, then system has no solution. So here there is no row of this form in this row echelon form, therefore given system has a solution. And if system has solution, then we check for leading and free variables. If there is no free variable, system has unique solution, and if there is at least one free variable, then system has infinite number of solutions. So here we obtain two free variables, therefore given system has infinite number of solutions. Now to write down the infinite number of solutions, we first write down the system corresponding to row echelon form, and then we express leading variables in terms of free variables for each equation starting from the last equation. So in last equation, y is free leading variable, z is free variable. So first we express y in terms of z. Then we put value of y in equation 1. So we obtain this equation x minus w equal to minus 1. And then we express leading variable x in terms of free variable. So after writing the system corresponding to row echelon form, we have to express leading variables in terms of free variables. Once we express leading variables in terms of free variables, we will assign any real numbers to free variables. Here z and w are free variables, so we assign z equal to r, w equal to s, where r and s can be any real numbers. And then we express each of these variables in terms of r and s. X is w minus 1, therefore x is s minus 1, y is 2z. Because z is r, we have y equal to 2r, and z is r and w is s. So in this way we can write down the infinite number of solutions for system of linear equations using Gauss elimination method. In this lecture, we have discussed the case of Gauss elimination method with infinitely many solutions. So I hope you like this lecture. In upcoming lectures, we will do some more examples on Gauss elimination method. Thank you very much.